Hello there, and welcome to Simple Sleepy Science. Tonight, we drift into tornadoes. And right now, the air around you carries the same invisible forces that create these spinning wonders. The wind outside your window, the breeze that moves through your room, they're all part of the same atmosphere that can twist into nature's most elegant spirals. But here's what most people don't know. Tornadoes aren't the monsters we imagine. They're conversations, dialogues between different kinds of air, meeting and dancing in ways that create something extraordinary. Tonight, we explore the hidden gentleness in Earth's wildest weather. This is a place for calm curiosity, for discovering that even powerful things follow simple, beautiful rules. So settle in, get comfortable, let the day fall away. We're about to learn why tornadoes, when you really understand them, can actually help you sleep. If this brings you calm, if you enjoy these quiet journeys through science, I'd love for you to join our community of night learners. Hit that like button and subscribe so you don't miss tomorrow's restful exploration. And leave a comment. Let me know where you're watching from and what time it is there. It helps me know I'm keeping you company across all these time zones. It starts with something so ordinary you barely notice it. Warm air and cold air, that's all. Two different temperatures existing in the same sky. The warm air is light, full of energy, eager to rise. It's been heated by the sun touching the ground, warming fields and parking lots and rooftops until the air above them grows restless. This warm air wants to climb. It wants to go up and up, carrying all that heat toward the cooler parts of the atmosphere. Meanwhile, cold air is heavy. It sinks. It falls. It's content to stay low, pressing down with its weight, dense and settled. When these two meet, something has to give. Picture it like this. Imagine you're in a room where one side is warm and the other is cold. The warm side wants to trade places with the cold side. They start to move past each other, sliding and shifting. But they don't move smoothly. They tumble, they spin. The warm air pushes up, the cold air pushes down, and where they brush against each other, they start to rotate. This rotation is gentle at first, just a slow turning, like stirring honey in a jar. But under the right conditions, that gentle turn can tighten. It can focus. It can become something more. Now, this atmospheric dance is happening somewhere on Earth right now. Above a field in Oklahoma, over the plains of Argentina, across the flatlands of Bangladesh. Warm air is rising, cold air is falling. And in their meeting, in their conversation, the seeds of rotation are planted. Most of the time, nothing comes of it. The air mixes and settles and the moment passes. But sometimes, when the conditions align just right, when the wind at different heights starts blowing at different speeds, when moisture fills the air and thunderstorms tower into the sky, that gentle rotation finds focus. It tightens. It stretches. It reaches down from the clouds toward the earth. And a tornado is born from nothing more than air talking to air, warm meeting cold, in a conversation as old as weather itself. Here's something that might surprise you. Most tornadoes could fit inside a grocery store parking lot. That's it. Not the mile-wide monsters you see in movies. not the massive funnels that swallow entire towns. The average tornado is only about 50 to 100 yards wide. Picture your street, the distance from your house to your neighbor's house across the way. That's the width we're talking about. A single house, maybe two houses side by side. That's the scale of most tornadoes. This changes everything about how we think of them. When you imagine a tornado, you probably see something huge, something that fills the whole sky. But the reality is far more intimate. Stand in the middle of a football field and look at the goalposts on one end. A typical tornado wouldn't even reach from sideline to sideline. It would touch down in a space you could walk across in less than a minute. This isn't to say they're harmless. Even a small tornado carries serious power. But understanding their true size makes them less overwhelming. Less like unstoppable forces, and more like focused points of energy. Think about your neighborhood right now. Your street, your block, the park down the road. A tornado passing through would affect just a narrow path. Houses on one side of the street might see damage, while houses on the other side stay untouched. Trees in one yard might be bent, while trees 3 doors down stand perfectly still. This precision, this narrow focus, is one of the most consistent features of tornadoes. They don't carpet bomb landscapes. They draw thin lines across them. The widest tornado ever recorded was 2.6 miles across. It happened in Oklahoma in 2013, and it remains extraordinary precisely because it was so unusual. That tornado made headlines around the world because tornadoes simply don't get that big. It was an outlier, a statistical extreme. The vast majority stay small. They touch down, they spin, they lift back up, all within a space you could throw a baseball across. When meteorologists talk about tornado damage paths, they measure them in yards, not miles. A typical path might be 50 feet wide. That's narrower than most 2-lane roads. This small scale reveals something important about how tornadoes work. They're not broad systems like hurricanes that span hundreds of miles. They're concentrated, focused. All that spinning energy gets compressed into a tight column. And because they're so narrow, they're also incredibly particular about where they touch. A tornado might destroy one barn and leave the barn next to it untouched. It might tear the roof off one side of a house, while the other side barely loses a shingle. This isn't random. It's just the reality of something so small moving across the land. So, when you picture a tornado now, make it smaller in your mind. Shrink it down. See it for what it usually is. A spinning column no wider than your local coffee shop. Contained and discreet. Powerful but limited in reach. This accurate scale doesn't make them less impressive. It makes them more real, more understandable, less like movie special effects, and more like actual weather, following actual physics, in actual small spaces, on an Earth that's mostly calm, mostly still, mostly peaceful as you rest tonight. Scientists measure tornado strength using something called the Enhanced Fujita Scale. It runs from EF0 to EF5. And here's the comforting part. Most tornadoes never get past EF1. They stay at the bottom of the scale, in the gentlest categories, where their power is real but limited. An EF0 tornado has winds between 65 and 85 miles per hour. That's about the speed of a car on the highway. These tornadoes can peel off some roof shingles, snap small branches, and push over shallow-rooted trees. But they can't level buildings. They can't destroy solid structures. They're the whispers of the tornado world. EF1 tornadoes are slightly stronger, with winds between 86 and 110 miles per hour. They can strip roofs, break windows, and overturn mobile homes. They're serious weather events, but they're not the apocalyptic forces of disaster movies. Most damage from an EF1 is repairable. Most structures stay standing. And here's the key fact. About 70% of all tornadoes fall into these first two categories. 7 out of 10 tornadoes are F2 or EF1. They come, they cause some damage, they leave. The majority of tornadoes are nature's lighter touch. EF2 tornadoes start to show real strength. Winds between 111 and 135 miles per hour. These can tear roofs completely off houses, destroy mobile homes, and snap large trees. About 20% of tornadoes reach this level. They're significant, but still far from the worst. EF3 brings winds up to 165 miles per hour. These can demolish well-built homes, flip cars, and strip bark from trees. Only about 5% of tornadoes get this strong. Already, we're in rare territory. EF4 tornadoes are devastating. Winds up to 200 miles per hour. They can level sturdy houses, throw vehicles hundreds of yards, and strip asphalt from roads. Less than 1% of tornadoes reach EF4 strength. They're statistical outliers, and EF5, the top of the scale, represents winds over 200 miles per hour. These are the tornadoes that make history. They're so rare that decades can pass between them. Since 1950, fewer than 60 tornadoes in the United States have been rated EF5. Out of tens of thousands of tornadoes total, only a handful have reached this level. What this means is simple. When a tornado forms, the odds overwhelmingly favor it staying weak. The chances that any given tornado will be catastrophic are tiny. Most will spin out their brief lives at the lower end of the scale, causing manageable damage to small areas before dissipating. This isn't luck. It's how the physics work. Creating a violent tornado requires perfect conditions, rare alignments of temperature, moisture, wind shear, and timing. Most storms can't generate that combination. They make tornadoes, yes, but gentle ones, brief ones, small ones. The Fujita scale gives us perspective. It turns vague fear into specific categories. It shows us that tornado strength follows a pattern, with most clustering at the weak end and only rare exceptions reaching the strong end. This knowledge doesn't eliminate the danger, but it transforms it from unknown terror into understood risk, measured and categorized, studied and predictable, part of a system that makes sense even as it spins. Scientists measure tornado strength using something called the Enhanced Fujita Scale. It runs from EF low to EF5. And here's the comforting part. Most tornadoes never get past EF1. They stay at the bottom of the scale, in the gentlest categories, where their power is real but limited. An AF tornado has winds between 65 and 85 miles per hour. That's about the speed of a car on the highway. These tornadoes can peel off some roof shingles, snap small branches, and push over shallow-rooted trees. But they can't level buildings. They can't destroy solid structures. They're the whispers of the tornado world. EF1 tornadoes are slightly stronger, with winds between 86 and 110 miles per hour. They can strip roofs, break windows, and overturn mobile homes. They're serious weather events, but they're not the apocalyptic forces of disaster movies. Most damage from an EF1 is repairable. Most structures stay standing. And here's the key fact. About 70% of all tornadoes fall into these first two categories. 7 out of 10 tornadoes are EF0 or EF1. They come, they cause some damage, they leave. The majority of tornadoes are nature's lighter touch. EF2 tornadoes start to show real strength. Winds between 111 and 135 miles per hour. These can tear roofs completely off houses, destroy mobile homes, and snap large trees. About 20% of tornadoes reach this level. They're significant, but still far from the worst. EF3 brings winds up to 165 miles per hour. These can demolish well-built homes, flip cars, and strip bark from trees. Only about 5% of tornadoes get this strong. Already, we're in rare territory. EF4 tornadoes are devastating. Winds up to 200 miles per hour. They can level sturdy houses, throw vehicles hundreds of yards, and strip asphalt from roads. Less than 1% of tornadoes reach EF4 strength. They're statistical outliers, and EF5, the top of the scale, represents winds over 200 miles per hour. These are the tornadoes that make history. They're so rare that decades can pass between them. Since 1950, fewer than 60 tornadoes in the United States have been rated EF5. Out of tens of thousands of tornadoes total, only a handful have reached this level. What this means is simple. When a tornado forms, the odds overwhelmingly favor it staying weak. The chances that any given tornado will be catastrophic are tiny. Most will spin out their brief lives at the lower end of the scale, causing manageable damage to small areas before dissipating. This isn't luck. It's how the physics work. Creating a violent tornado requires perfect conditions, rare alignments of temperature, moisture, wind shear, and timing. Most storms can't generate that combination. They make tornadoes, yes, but gentle ones, brief ones, small ones. The Fujita scale gives us perspective. It turns vague fear into specific categories. It shows us that tornado strength follows a pattern, with most clustering at the weak end and only rare exceptions reaching the strong end. This knowledge doesn't eliminate the danger, but it transforms it from unknown terror into understood risk, measured and categorized, studied and predictable, part of a system that makes sense even as it spins. Tornadoes are artists in a strange way. They paint themselves with whatever they touch. A tornado has no color of its own. The funnel itself is just spinning air, and air is invisible. But as it moves across the ground, it picks up debris, dust, soil, and moisture. And these materials give it color. A tornado crossing. Red clay farmland turns rusty orange, carrying the earth into the sky like a living sculpture. One moving through an area with dark, rich soil becomes deep brown, almost black, a column of shadow against grey clouds. In areas with light-colored sand or pale dirt, tornadoes can appear almost white or tan, ghostly and ethereal. When a tornado stays aloft, never quite touching the ground, it often looks grey or translucent. These are the condensation funnels, made visible by water droplets forming in the low-pressure core. They're clouds shaped into spirals, but the moment they touch Earth, they change. They become whatever the Earth gives them. This transformation happens in seconds. A pale funnel descends, makes contact, and suddenly blooms with color as dust and debris rush upward into the rotation. Some tornadoes appear almost white because they're filled with hail and ice. These form in the coldest parts of severe storms, where frozen precipitation gets caught in the spinning winds. The ice reflects light, making the whole funnel gleam like a column of frozen motion. Other tornadoes take on a greenish tint, not from the tornado itself, but from the storm behind it. Severe thunderstorms sometimes cast a green light when sunlight filters through massive amounts of water and ice. A tornado descending from a green-lit storm can carry that eerie color with it. Red tornadoes are common in places like Oklahoma and Kansas, where the soil is iron-rich and rust-colored. These tornadoes look like they're made of fire or blood, dramatic against the landscape. In the Great Plains, where black topsoil dominates, tornadoes turn dark as ink, sometimes so black. They're hard to distinguish from the storm clouds above them. This camouflage makes them particularly dangerous. People might not see them coming because the tornado blends perfectly with the dark sky behind it. After heavy rain, tornadoes can appear almost blue-gray, filled with water and mist. These rain-wrapped tornadoes are shrouded in sheets of precipitation, making them look less like distinct funnels and more like dark masses descending from the clouds. They're often wider looking than they actually are, because the rain around them obscures their true shape. In desert regions, tornadoes pick up light sand and dust, turning pale yellow or beige, like pillars of sandy wind connecting earth to sky. Each tornado becomes a portrait of where it travels. It carries the signature of the land beneath it, wearing the earth's colors as it spins. This quality makes every tornado unique. No two look exactly alike, because no two touch the same ground in the same way. They're temporary art pieces, collaborations between wind and earth, taking form and color from their surroundings before releasing everything back down when they dissipate. The dirt falls, the debris settles, and the invisible air returns to being just air again, clear and colorless, as if the painting never existed. The sound of a tornado isn't what you'd expect. Everyone talks about the freight train roar, that deep rumbling that shakes the ground and fills the air. And yes, large tornadoes do sound like that, but many tornadoes make almost no sound at all. Small tornadoes, especially those that stay over open ground or move through areas without many structures, can be remarkably quiet. Just a soft rushing, like wind moving through leaves. Some witnesses report hearing nothing unusual until the tornado was directly overhead. The silence is unnerving in its own way, more unsettling than any roar, because it contradicts every expectation. This quietness happens for a simple reason. Sound comes from things interacting. A tornado by itself is just spinning air. Air moving through air doesn't make much noise. It's only when that air starts hitting objects that sound emerges. A tornado tearing through a forest creates noise because it's snapping branches, uprooting trees, grinding wood against wood. A tornado ripping apart buildings roars because it's shattering glass, twisting metal, and throwing debris against other debris. But a tornado moving across an empty field generates surprisingly little sound. The wind spins, the grass bends, and everything stays relatively quiet. Even the famous freight train sound isn't universal. It depends entirely on what the tornado encounters. The rumble comes from the combined noise of destruction, all those individual impacts and collisions, blending together into one continuous roar. Take away the objects to destroy, and you take away much of the sound. This is why tornadoes over open water or bare ground often go unnoticed, except by those who see them. They're visible as rotating columns, clear funnels connecting sky to surface, but they're acoustically subtle. You might hear the parent thunderstorm rumbling overhead. You might hear rain and wind, but the tornado itself doesn't announce its presence with volume. The quiet tornadoes are often the weaker ones, the EF0 and EF1 varieties that lack the raw power to generate intense sound. Their winds aren't strong enough to create the violent collisions that produce noise. They spin gently by tornado standards, rotating in relative peace. Some people who've witnessed these quiet tornadoes describe them as almost meditative to watch, if you can set aside the danger. A column of wind, visible but silent, moving across the landscape like a ghost. There's also the matter of distance. The roar of a strong tornado doesn't carry far. Sound dissipates quickly in open air, especially irregular sound like the chaos of destruction. You might be a mile away from a massive, roaring tornado and hear nothing but distant thunder. The sounds that do carry are often the secondary effects, the crackling of power lines, the shattering of transformers, the rumble of collapsing structures. But the tornado's core sound, that tight column of spinning wind, stays localized. It's there if you're close, absent if you're not. So, the next time you imagine a tornado, don't automatically add the soundtrack of apocalyptic noise. Some tornadoes whisper, some barely make a sound louder than a strong breeze. They prove that nature's power doesn't always announce itself with volume. Sometimes it arrives quietly, spinning and moving through the world with nothing more than a gentle rush of air. Tornadoes have cousins that live over water. They're called waterspouts, and they're generally gentler than their land-based relatives. A waterspout is just a tornado that forms over a lake, ocean, or any body of water. The physics are identical. Rotating air, low pressure core, visible funnel. But waterspouts tend to be weaker and shorter lived. Most never reach the intensity of even a modest land tornado. They're nature's way of showing tornado physics in a softer form, like a sketch before the final painting. There are two types of waterspouts. Fair weather waterspouts form on relatively calm days, when the water is warm and the air above it is cooler. These develop from the water surface upward, starting as swirls on the water that gradually stretch toward the clouds. They're typically weak, with winds rarely exceeding 50 miles per hour. They last 10 to 15 minutes on average, dancing across the water's surface before dissipating. You can watch them from shore in relative safety. They're beautiful, almost hypnotic, like ribbons of mist connecting sea to sky. The second type are tornadic waterspouts. These are actual tornadoes that either form over water or move from land onto water. They're stronger and more dangerous than fair weather waterspouts, but even these are usually weaker than tornadoes over land. Water provides less friction than earth. There's nothing to slow the winds at the surface, but there's also nothing to provide the kind of instability that creates the strongest tornadoes. The result is a compromise, rotation that's visible and real, but generally less intense. Waterspouts look graceful in a way land tornadoes rarely do. They're often thinner, more delicate in appearance. The spray of water they kick up creates a skirt around the base, a circular fan of mist that makes the whole structure look like it's dancing. Sunlight passing through the spray can create rainbows, adding color to the gray funnel. From a distance, especially over tropical waters, waterspouts can appear almost decorative, like nature's ornaments hung between ocean and cloud. Boats that encounter waterspouts generally survive if they're not too close. The winds can be strong enough to damage sails or rock a vessel, but the narrow width means exposure is brief. Many sailors report passing near waterspouts without serious incident, though they certainly don't seek them out. The danger is real, but it's manageable in ways that land tornadoes are not. You can see them coming from far off, change course, and avoid them entirely. On land, tornadoes can hide behind rain or hills. On water, the view is clear. Waterspouts are common in tropical and subtropical waters. The Florida Keys see hundreds each year, especially during summer when warm water meets cooler air masses. They form, they move, they vanish, often with no one but fishermen and boaters witnessing them. Most never make the news because they affect no structures and harm no one. They exist as pure phenomena, spinning above water, brief and beautiful, doing no damage beyond stirring the surface of the sea. They're reminders that tornado dynamics don't require destruction. The physics work just fine over empty water, creating rotation for its own sake, elegant and temporary, before returning the energy to the atmosphere and leaving the ocean calm once more. Every tornado eventually reaches its final form. It's called the rope stage, and it's when the tornado is weakest, winding down, returning its energy to the sky. The wide funnel narrows, the thick column thins. What was once a solid cone of spinning air becomes something delicate and serpentine. It looks like a rope hanging from the clouds, twisting and curling as it dissipates. This stage is the tornado's goodbye, its slow fade from power into nothing. And visually, it's often the most beautiful phase. The transformation happens because the parent storm is losing strength. The updraft that fed the tornado weakens. The rotation slows. Without that constant supply of energy, the tornado can't maintain its structure. It stretches thin, like taffy being pulled. The funnel elongates, becoming narrower and more contorted. Sometimes it looks like a twisted piece of string, looping and kinking as different parts of it slow at different rates. The tight organization falls apart. What remains is a ghostly remnant, still spinning but barely, During the rope stage, the tornado is at its least dangerous. The winds have dropped significantly. The funnel might still be touching the ground, but it's causing minimal damage. Trees might sway, dust might kick up, but the destructive power is gone. This is the tornado in its final minutes, sometimes its final seconds. Photographers love the rope stage because the shapes are so dramatic. The thin funnel creates elegant curves against the sky, twisting in ways that seem almost intentional, like calligraphy written in wind. Sometimes the rope stage tornado lifts off the ground entirely while still visible in the air. The bottom of the funnel pulls up, retracting into the cloud base like a thread being pulled into fabric. The rotation continues aloft for a while, invisible at ground level, but still present higher up. Eventually, even that dissipates. The winds blend back into the general storm circulation. The tornado ceases to exist. What was once a focused column of energy becomes diffuse, scattered, ordinary air once again. Not every tornado goes through a clear rope stage. Some dissipate quickly, collapsing from full strength to nothing in moments. Others maintain their width until the very end, then suddenly vanish. But when the rope stage does occur, it's a clear signal that the danger is passing. Storm chasers know that a roping tornado is a dying tornado. They can move closer, adjust their position, and capture images without the same level of risk. The tornado is still there, but it's winding down, losing the battle against entropy. There's something poetic about this ending. The tornado doesn't explode or shatter. It simply thins until it's no longer there. It becomes less and less substantial, less and less organized, until the distinction between tornado and regular wind disappears entirely. The energy that created it spreads out, redistributes, and rejoins the larger patterns of the atmosphere. The rope stage is the visible proof that even powerful systems move toward rest. They can't sustain intensity indefinitely. Eventually, they soften, they slow, they become threads, and then they become nothing, leaving the sky clear and the air calm, as if nothing extraordinary ever happened at all. Most of Earth never sees a tornado. The conditions required are so specific, so precise, that vast regions of the planet have never recorded one in all of human history. You need warm, moist air at the surface. You need cold, dry air aloft. You need wind shear, where winds at different heights blow at different speeds and directions. You need instability in the atmosphere, and you need all of these things to happen in the same place at the same time. That's a tall order. Most places can't meet it. Look at a map of global tornado occurrence. The United States dominates, particularly the Central Plains. But even there, any single location might see a tornado only once every few decades, if that. Your specific address, your exact house, the odds of a tornado passing directly over it are astronomically small. In many parts of the world, those odds drop to nearly zero. Europe gets a few dozen tornadoes per year across the entire continent. Asia sees some, mostly in Bangladesh and parts of China. But compared to the landmass involved, they're rare events. Africa has very few tornadoes. The atmospheric setup doesn't favor them. South America gets some in Argentina and southern Brazil, but again, they're uncommon. Australia sees tornadoes occasionally, but nothing like the frequency of North America. Antarctica has never recorded a tornado, and likely never will. The Arctic sees none. The middle of oceans, despite having water to fuel storms, lack the land-based heating contrasts that help create the conditions tornadoes need. Deserts are mostly tornado-free because they lack moisture. Rainforests have plenty of moisture, but lack the strong wind shear. Mountains disrupt the atmospheric flow that tornadoes require. Even in Tornado Alley, the heart of tornado country, most towns go years without seeing one nearby. The alley is broad, stretching from Texas through Oklahoma, Kansas, and into Nebraska and South Dakota. But within that region, tornadoes are still selective. They form where conditions align on a particular day, often in corridors just a few miles wide. One county might get hit, while the county next door sees nothing. The randomness within the pattern means safety is the norm, even in areas known for tornadoes. This rarity makes tornadoes exceptional rather than ordinary. They're not like rain that falls everywhere, or wind that blows in every region. They're specialists, requiring a unique recipe that most places can't provide. If you live outside the primary tornado zones, your chances of ever experiencing one firsthand are vanishingly small. And even if you live inside those zones, the odds still favor you never seeing one. The Earth is huge. Tornadoes are tiny and brief. The math works in your favor. This perspective matters for peace of mind. Tornadoes feel universal because they get so much attention when they occur. But they're actually quite limited in where and when they happen. Most of the world sleeps safely, never worrying about rotating storms because rotating storms don't happen there. The atmosphere over most of the planet is too stable, too dry, too something to make tornadoes possible. And even where they are possible, they're still rare enough that most people will live entire lives without encountering one, protected by simple geography and the laws of probability that make tornado conditions more the exception than the rule. Tornadoes serve a purpose in the larger system. They're not chaos, they're corrections. When one part of the atmosphere gets too warm and another part gets too cold, Earth needs to balance things out. Heat wants to spread, cold wants to sink and fill in. The atmosphere is constantly trying to reach equilibrium, and sometimes that process creates tornadoes. They're the planet's way of mixing things up, redistributing energy that's become too concentrated in one place. Think of them as Earth's pressure release valves, intense but necessary. The atmosphere is always uneven. The equator receives more sunlight than the poles. Land heats faster than water. Cities create heat islands. All this creates pockets of warmth and cold scattered across the globe. The atmosphere responds by moving air from hot zones to cold zones, trying to even things out. Most of this happens through gentle processes, like steady winds and gradual pressure changes. But sometimes the imbalance is sharp. Hot air butts directly against cold air with no gradual transition. That's when the atmosphere turns violent, creating thunderstorms and tornadoes to force the mixing. A tornado is essentially a small-scale energy transfer. Hot air at the surface needs to rise. Cold air aloft needs to sink. The rotation develops as a way to accomplish this efficiently. The spinning column acts like a conveyor belt. rapidly moving air vertically. Warm air shoots up through the core. Cold air wraps around the outside and descends. In just a few minutes, a tornado can move enormous amounts of energy from ground level to the upper atmosphere. It's fast, efficient, and effective at restoring balance. This reframing changes how we see them. Tornadoes aren't the atmosphere breaking down. They're the atmosphere working, just in an extreme way. The same physics that creates a gentle breeze on a spring day can create a tornado when the energy difference is large enough. It's all the same system, just operating at different intensities. The atmosphere doesn't distinguish between good weather and bad weather. It only knows imbalance and the drive to fix it. Tornadoes are one tool in that toolkit. Every tornado that forms removes energy from the system. It takes heat out of the lower atmosphere and deposits it higher up. It mixes layers that were separated. When it dissipates, the atmosphere in that area is slightly more balanced than before. The job is done. The correction is made. This doesn't mean tornadoes are gentle or safe, but it means they fit into a larger pattern. They're not random acts of destruction. They're responses to specific conditions, and those responses help maintain the overall health of the atmospheric system. You can see this on a weather map. Areas prone to tornadoes are areas where cold fronts from Canada push into warm, humid air from the Gulf of Mexico. The contrast is stark. The atmosphere can't handle that sharp boundary peacefully. So it creates storms, and some of those storms spawn tornadoes. Those tornadoes do damage, yes, but they also accomplish the mixing that needs to happen. They're part of how Earth keeps itself from developing even larger, more dangerous imbalances. In a strange way, tornadoes prevent worse weather by releasing energy in focused bursts rather than letting it build to catastrophic levels across entire regions. Most tornado warnings turn out to be nothing. The alarm goes off, the sirens sound, people take shelter, and then the storm passes without producing a tornado. This happens more often than not. The false alarm rate for tornado warnings sits around 70%. 7 out of 10 warnings end with no tornado. Some people find this frustrating, but it's actually a sign the system is working exactly as intended. Meteorologists would rather warn you about a tornado that doesn't form than fail to warn you about one that does. The reason for all these false alarms is simple. Weather prediction is hard, really hard. Meteorologists can identify storms that have the potential to produce tornadoes. They can see rotation developing in the clouds. They can measure wind shear and instability. But they can't know for certain whether that rotation will tighten into a tornado and descend to the ground. The atmosphere is too complex, too chaotic. Tiny variables make huge differences. So when conditions look dangerous, the warning goes out, even though the odds of an actual tornado remain uncertain. This uncertainty doesn't mean the warnings are wrong. A storm that looks tornadic might produce a tornado 5 minutes after you take shelter. Or it might weaken before the rotation reaches the ground. Both outcomes are possible until the moment resolves itself. The warning reflects the danger level, not a guaranteed prediction. It's saying this storm could kill you. Take it seriously, and that's appropriate. The consequences of missing a real tornado far outweigh the inconvenience of a false alarm. Technology has gotten better at detecting tornado signatures. Doppler radar can see rotation inside storms from miles away. It measures wind speed and direction at different altitudes. When the radar shows a tight couplet of winds moving in opposite directions, that's a strong indication of rotation. But indication isn't certainty. The rotation might be happening too high up. It might be too weak to reach the ground. The storm might be falling apart even as the warning is issued. Meteorologists see the signs and make the call, knowing they'll be wrong more often than right, but accepting that trade-off to keep people safe. The false alarms also serve another purpose. They keep people practiced. If warnings only sounded when tornadoes were guaranteed, people might never experience one and wouldn't know how to respond. The regular warnings, even the false ones, reinforce the routine. They remind people where their shelter is. They test the alert systems. They maintain awareness. Communities in tornado-prone areas learn not to panic at every warning, but also not to ignore them. They develop a measured response, checking conditions, staying alert, ready to take cover if needed. So when you hear a PAL, tornado warning, and nothing happens, that's not failure. That's the system protecting you with extra caution. The sky was watched. The data was analyzed. The danger was real enough to warrant action, even if it didn't materialize this time. And the fact that most warnings are false alarms means that the threshold for warning is low, which is exactly where it should be. Better to take shelter unnecessarily than to be caught unprotected when the one real tornado in 10 warnings touches down in your area. Tornadoes have tiny cousins that appear on ordinary sunny days. They're called dust devils, and they're everywhere. You've probably seen them without knowing what they were. A small spinning column of dust crossing a parking lot. A whirl of leaves in a field. A little spiral of dirt on a baseball diamond. These are dust devils, and they form from nothing more than hot ground and a light breeze. No thunderstorm needed, no cold front required. Just sunshine and pavement or dry dirt, creating tiny pockets of rotation that last a few seconds or minutes before falling apart. Dust devils form when the ground heats unevenly. A patch of asphalt gets hotter than the grass next to it, or a bare spot of dirt warms faster than the surrounding area. The air directly above that hot spot rises quickly. Cooler air rushes in from the sides to replace it. If there's any rotation in that incoming air, even the tiniest spin, it gets concentrated as the air spirals upward. The result is a miniature vortex, a baby tornado without the storm. Most dust devils are only a few feet wide and maybe 10 or 20 feet tall. They're harmless. You can walk through one and barely feel it. But some dust devils grow larger. In deserts, where the ground gets intensely hot, dust devils can reach several hundred feet tall and spin with winds up to 60 miles per hour. These are rare and can be strong enough to damage tents or blow over porta potties, but they're still far weaker than real tornadoes. They look impressive, like something out of a movie, tall columns of dust rising into clear blue skies. But they form in fair weather, dissipate quickly, and pose minimal danger. They're playful versions of tornado physics, demonstrations that spinning air is normal and common. There are other small worlds too. Waterspouts can form on hot days over lakes without any storm present, similar to dust devils, but over water. Landspouts are weak tornadoes that form in ways similar to dust devils, but under developing thunderstorms, bridging the gap between the two phenomena. Fire whirls develop during wildfires when intense heat creates rotation. Steam devils rise from the surface of lakes when cold air moves over warm water. All of these are rotating columns of air, miniature versions of the same physics that creates tornadoes, but gentle and usually harmless. The existence of these small whirls is comforting in a way. They show that rotation is natural. It happens all the time at small scales without danger. The atmosphere loves to spin when given the chance. Most of that spinning stays small and weak because the energy isn't there to make it grow. A dust devil is what you get when you have a little heat and a little spin. A tornado is what you get when you have massive heat, massive instability, and massive wind shear all at once. The principle is the same, only the scale differs. Next time you see dust swirling in a parking lot, or leaves spinning in a tight circle on a calm day, you're watching the same physics that creates tornadoes, just smaller, gentler, harmless. It's a reminder that the spinning air we fear is really just air doing what air does, responding to heat and pressure, following simple rules, usually creating nothing more threatening than a momentary whirl of dust that dissipates as quickly as it formed. The center of a tornado is calm. Not calm like peaceful, but calm like empty. The core has lower pressure than the spinning walls around it. The fastest winds aren't at the center. They're in the wall of the funnel, where air is moving at maximum speed. The very middle is almost still by comparison. It's a paradox. The most violent part of the storm surrounds a center that's relatively quiet. This phenomenon is similar to the eye of a hurricane, but much smaller and harder to define clearly. The low pressure at the center is what drives the whole system. Air rushes toward low pressure. It spirals inward, accelerating as it gets closer to the core. But it can't reach the center directly because the rotation throws it outward. So the air keeps circling, trapped in a tight spiral around a hollow middle. That hollow is the calm. It's not a large space. In most tornadoes, the calm center might be only a few feet wide, maybe 10 or 20 feet in stronger tornadoes. It's barely noticeable because the tornado moves so quickly that you'd pass through the center in a fraction of a second. People who've survived being inside tornadoes sometimes report a moment of eerie stillness. The wind stops, the noise drops, everything goes quiet and still. Then the other side of the tornado hits and the violence resumes. This brief pause is the center passing over. It lasts seconds at most. The experience is disorienting. Your brain barely has time to register the calm before chaos returns. But those who notice it describe it as surreal, a pocket of peace in the middle of destruction. The physics behind this calm is straightforward. In any rotating system, the center experiences less movement than the edges. Spin a bucket of water, and the water climbs up the sides while a depression forms in the middle. The center is where all the motion is aimed, but because everything is spinning around it, rather than through it, it stays relatively clear. A tornado's center works the same way. The winds circle around it at high speed, but the center itself is a zone of lower wind speed and lower pressure. This doesn't make the center safe. The low pressure itself can cause damage. Buildings can explode outward when the pressure inside them is suddenly much higher than the pressure outside. Ears pop, windows burst. The pressure difference is extreme, even if the winds are temporarily calm. And the calm only lasts while the center is directly overhead. A step in any direction puts you back in the violent winds. The center is too small, and the tornado moves too fast for the calm to matter in practical terms. But knowing it exists adds dimension to how we understand tornadoes. They're not solid masses of wind. They're hollow tubes, spinning walls around a quieter core. This structure makes them more comprehensible. They're organized. They follow patterns. Even in their power, they have geometry, structure, a center point around which everything revolves. The calm at the core is a reminder that even in nature's most dramatic systems, there's order. There's a point of reference, a still place at the heart of the motion, even if that stillness is almost impossible to perceive while the tornado tears through its brief, violent life. Every tornado teaches scientists something. Even the smallest ones add data to the collective understanding. Researchers study the storms that produce them, the atmospheric conditions present, the radar signatures, the damage patterns left behind. Each tornado is a natural experiment, showing how theory translates to reality. This information feeds back into forecasting models, warning systems, and building codes. Over decades, thousands of tornadoes have contributed to a body of knowledge that makes everyone safer. They're destructive, yes, but they're also educational in ways that controlled experiments could never replicate. After a significant tornado, teams of scientists visit the damage path. They're called damage survey teams, and they walk the entire length of the tornado's track, documenting everything. How trees fell, which walls of buildings collapsed first, what kinds of debris traveled how far. They assign the enhanced Fujita rating based on what they find. But more importantly, they learn about how tornadoes interact with structures. This knowledge improves construction standards. Engineers discover which building techniques work and which fail. New building codes emerge from these lessons, requiring stronger anchors, better roof attachments, reinforced walls in vulnerable areas. The radar data from each tornado helps refine detection algorithms. Meteorologists compare what the radar showed before the tornado with what actually happened. They look for patterns. Maybe a certain type of rotation signature reliably leads to tornadoes. Maybe another type usually fizzles out. These correlations get built into the software that issues warnings. The system learns from every event, becoming slightly better at distinguishing real threats from false alarms. The improvement is gradual, but it's real. Warning lead times have increased. Accuracy has improved. Lives have been saved because past tornadoes taught the system what to look for. Scientists also study tornado formation itself. How does rotation in a thunderstorm tighten into a tornado? Why do some storms produce multiple tornadoes, while others produce none? What triggers the final descent to the ground? These questions don't have complete answers yet. Every tornado offers clues. Mobile radar units now drive into storms, taking measurements from dangerously close range. Weather balloons and aircraft gather data from inside tornadic storms. Slowly, the picture becomes clearer. The understanding deepens. And with understanding comes better prediction and better protection. Long-term tornado records reveal climate patterns. Scientists track where tornadoes occur, when they occur, and how strong they are. Over decades, trends emerge. Some areas see more activity, others see less. Tornado season shifts slightly. These patterns help communities prepare. If tornadoes are becoming more common in a region, that affects planning decisions, insurance requirements, and public awareness campaigns. The data transforms tornadoes from random disasters into predictable risks that can be managed and mitigated. There's something almost redemptive in this. Tornadoes cause harm, but the harm isn't wasted. It becomes knowledge. That knowledge protects future generations. Every damaged building teaches engineers how to build stronger. Every missed warning teaches meteorologists how to detect better. Every tornado that forms adds to the database that makes the next one more predictable. The destruction serves a purpose beyond itself. It contributes to a collective learning process that slowly but steadily reduces the threat tornadoes pose, turning chaos into data and data into safety for the people who come after. Storm chasers have changed how we see tornadoes. Before photography and video became widespread, tornadoes were described through words alone, often exaggerated by fear and poor visibility. Now, we have thousands of images and videos showing exactly what tornadoes look like. The structure, the motion, the variety. These images reveal beauty alongside danger. Storm chasers position themselves at safe distances with telephoto lenses, capturing tornadoes in sharp detail against prairie skies. The photos show tornadoes as sculptural forms, temporary structures with their own geometry and grace. The best tornado photographs look almost artistic. A white funnel against dark clouds, a rope stage tornado catching golden sunset light, multiple vortices dancing around a central column. These images circulate widely, appearing in documentaries, textbooks, and museums. They've demystified tornadoes by making them visible. People can study the images, see the details, understand the structure. What was once terrifying and unknown becomes familiar, still dangerous, but no longer mysterious. The act of seeing clearly reduces fear. Storm chasers contribute more than just pretty pictures. They provide ground truth for meteorologists. When a tornado forms, chasers on location can confirm it immediately, giving warnings real-time verification. They report the tornado's location, movement, cause, and behavior. This information helps emergency managers make decisions about sirens, evacuations, and resource deployment. The chasers act as eyes on the ground, filling gaps that radar alone can't cover. A tornado might be hidden by rain on radar, but a chaser 3 miles away can see it clearly and report it. The dedication required for storm chasing is remarkable. Chasers drive thousands of miles each spring, following weather models and storm forecasts. They position themselves in the likely path of severe weather, then wait. Most days produce nothing. The storms fizzle or go the wrong direction or never develop rotation. But the chasers keep going back, driven by a mix of scientific curiosity, adrenaline, and the desire to document something extraordinary. When they do encounter a tornado, the footage they capture becomes part of the historical record. Future researchers study it. The public watches it. Understanding grows. Storm chasing has also become safer over time. Early chasers took enormous risks, driving too close or getting caught in rapidly changing situations. Modern chasers use GPS, live radar on mobile devices, and communication networks to coordinate and share information. They maintain escape routes. They understand storm behavior well enough to predict where the tornado will go. Fatal accidents still happen, but they're rare. Most chasers operate with practiced caution, respecting the power of what they're pursuing while staying far enough away to remain safe. The images they bring back serve a larger purpose. They help the public understand that tornadoes, while dangerous, are natural phenomena following physical laws. The photos show tornadoes as weather events, not supernatural monsters. This perspective helps communities prepare rationally rather than panic irrationally. When you've seen 100 tornado photos, each one different, but all following similar patterns, tornadoes become less abstract. They're real things with consistent characteristics. And real things, once understood, become manageable. The fear doesn't disappear entirely, but it transforms into respect, awareness, and appropriate caution rather than helpless terror. Tornadoes follow the calendar. They arrive with the seasons and leave when conditions no longer support them. In the United States, tornado season peaks in spring, typically April through June. This is when cold air from Canada still pushes south, while warm, humid air flows north from the Gulf of Mexico. The collision zone between these air masses creates the perfect setup. As spring progresses, the zone of maximum activity shifts northward. April sees peak tornado activity in the southern plains. By May, the focus moves to Oklahoma and Kansas. June brings the highest risk to the northern plains and Midwest. This predictable rhythm means tornadoes aren't random surprises scattered throughout the year. They cluster in specific months when atmospheric conditions favor their formation. Outside of peak season, tornadoes still occur, but far less frequently. Winter tornadoes are rare because cold air dominates most of the country, eliminating the warm-cold contrast needed. Summer tornadoes decrease because the jet stream, which provides wind shear, retreats far to the north. By late summer and fall, tornado activity drops to its lowest levels. The atmosphere settles into more stable patterns. The dramatic clashes of spring give way to calmer weather. Other parts of the world have their own tornado seasons. Argentina sees peak activity in spring and early summer, October through December in the southern hemisphere. Bangladesh experiences tornadoes during the pre-monsoon season in April and May. Europe gets most of its tornadoes in summer when warmth and moisture create instability. These patterns are as reliable as any seasonal weather. Farmers know when to plant based on seasonal rains. Communities in tornado zones know when to pay extra attention to the sky based on tornado climatology. The seasonal pattern also means long stretches of safety. If you live in tornado country and it's August, your risk is minimal. The setup simply isn't there. The atmosphere lacks the ingredients. You can watch thunderstorms roll through without worrying about rotation. Winter brings its own weather concerns, ice and snow and cold, but tornadoes aren't among them. For 8 or 9 months of the year, tornadoes are effectively off the table in most locations. The danger concentrates into a few weeks or months, then vanishes until next year. This regularity makes preparation easier. You know when to check your shelter. You know when to review your family emergency plan. You know when to keep a weather radio handy and pay attention to forecasts. Tornado season becomes part of the annual routine, like preparing for hurricane season in coastal areas or wildfire season in dry regions. The predictability removes some of the fear. It's not a constant threat looming every day. It's a seasonal risk that appears, peaks, and fades on a schedule that rarely varies by more than a few weeks. Tornadoes are woven into the Earth's annual cycle as surely as spring flowers and autumn leaves. They're part of the rhythm of the planet's weather systems, responding to the changing angle of sunlight and the seasonal movement of air masses. This makes them natural rather than aberrant. They're not glitches in the system. They're expected outcomes of seasonal conditions, arriving when the atmosphere sets the stage and departing when it doesn't. Understanding this pattern transforms tornadoes from unpredictable chaos into anticipated events that fit into the larger order of how weather works across the turning year. Tornadoes follow the same physics that makes figure skaters spin faster when they pull in their arms. It's called conservation of angular momentum, and it's one of the universe's fundamental rules. When something rotating gets smaller, it spins faster. When it spreads out, it slows down. A figure skater starts spinning with arms extended. Then they pull their arms in tight against their body. Suddenly, they're spinning much faster, sometimes so fast they blur. They didn't add energy. They just concentrated the rotation they already had into a smaller space. Tornadoes work exactly the same way. Air in a thunderstorm starts rotating in a broad, slow column. This initial rotation might be miles wide, turning gently. But as the updraft pulls air upward, the column narrows. The rotation that was spread across miles gets compressed into a space just hundreds of feet wide. The spin rate increases dramatically. What was a lazy rotation becomes violent. The air didn't gain new energy. It just concentrated the energy it had. The same amount of spin packed into a smaller space means much higher speed. This principle explains why tornadoes can have such extreme winds. The rotation starts mild and gets amplified purely through geometry. The narrower the funnel, the faster it spins. This is why the strongest tornadoes tend to be relatively compact. A mile-wide tornado, despite its size, often has slower wind speeds than a tornado a few hundred feet wide. The tight ones concentrate their rotation more effectively. They're the skater with arms pulled in tight. The wide ones are still dangerous, but their winds are spread across a larger area, reducing the maximum speed at any given point. The mathematics behind this is elegant. Angular momentum equals mass times velocity times radius. If radius decreases and mass stays constant, velocity must increase to keep the equation balanced. Nature doesn't violate this law. It can't. So, when a rotating column of air narrows, the wind speed automatically increases. No additional force required, just geometry and conservation laws doing their work. This predictability makes tornadoes comprehensible. They're not magic. They're physics playing out in real time. Understanding this principle reveals something comforting. Tornadoes are bound by rules. They can't spin faster than the physics allow. They can't violate conservation of energy or momentum. They're powerful, but they're not unlimited. The same laws that govern spinning skaters and rotating galaxies govern tornadoes. This puts them in context. They're part of the same physical universe as everything else, following the same mathematics, predictable in their behavior, even when dramatic in their effects. You can see this principle everywhere once you notice it. Water draining from a bathtub spins faster as it approaches the drain. Hurricanes have their fastest winds in the tight eye wall, not the broad outer bands. Galaxies spin faster near their centers. The universe loves this rule. It applies at every scale, from quantum particles to cosmic structures. Tornadoes are just one more example of rotation, conserving its momentum, concentrating as it narrows, following mathematics that were true before Earth existed and will remain true long after. There's something peaceful in that. Even the wildest weather obeys timeless laws, elegant and unchanging. Nature recovers from tornadoes faster than you'd expect. The cleared land becomes opportunity. Within weeks of a tornado passing through a forest, new growth appears. Seeds that were dormant in the soil suddenly have access to sunlight. They sprout. Small plants that couldn't compete under the shade of mature trees now have their chance. Grasses spread across the bare ground. Wildflowers bloom in spaces that were dark for decades. The destruction creates room for renewal, and nature fills that room quickly. Young trees grow faster in cleared areas, without competition from older, established trees. Saplings shoot upward with vigor. A forest that took 100 years to reach maturity might be replaced by a young forest in just 20 or 30 years. The new forest looks different, more uniform in age, but it's healthy and functional. Birds return, animals move back in. The ecosystem reconstitutes itself around the new structure. What seemed like permanent damage turns out to be temporary disruption in the larger timeline of forest succession. Tornado damage paths become ecological corridors. The mix of cleared land and standing timber creates edge habitat, the transition zones between different environments. Many species thrive in edge habitat. Deer find food in the new growth, while sheltering in the remaining forest. Birds that prefer open areas nest in the cleared sections. Birds that need trees stay in the undamaged areas nearby. The diversity actually increases for a time as the recovering area supports species from multiple habitat types simultaneously. Prairies and grasslands recover even faster. These ecosystems evolved with disturbance. Fire, grazing, wind, they're all part of the natural pattern. A tornado clearing a section of prairie isn't catastrophic. It's just another disturbance event. The grasses have deep roots that survive. They send up new shoots within days. The prairie looks damaged briefly, then bounces back, often more vigorous than before. The cleared patches sometimes bloom with more flowers the following spring, as if the tornado stirred something awake in the soil. Even the debris left behind serves a purpose. fallen trees become habitat for insects, fungi, and small mammals. They decay slowly, returning nutrients to the soil. The dead wood hosts beetles, which attract woodpeckers, which create cavities that other birds use. The cycle of decay and renewal happens whether humans clean up the debris or not. Nature processes it all, breaking down the destruction into building blocks for new life. Nothing is wasted. Everything feeds back into the system. This resilience offers perspective. Tornadoes look like endings, but they're really transitions. The landscape changes form but remains alive. The processes that made the forest or prairie in the first place are still operating. They rebuild what was lost, sometimes in different arrangements, but always moving forward. Nature doesn't mourn the trees that fell. It uses them. It grows around them. It finds advantage in the disruption and turns it into opportunity for the next generation of plants and animals. In a few decades, you might walk through a former tornado path and not know anything happened unless someone told you. The trees are slightly younger and more uniform, but the forest is whole again. The prairie is green. Life has filled every space the tornado emptied, proving that destruction, while real and significant, is temporary compared to the persistent force of growth and renewal that drives ecosystems forward through time. You're being watched over more carefully than you realize. A vast network of technology and people monitors the sky constantly, looking for conditions that could produce tornadoes. Doppler radar stations across the country scan the atmosphere every few minutes, measuring wind speed and direction at different altitudes. Satellites watch from space, tracking storm systems as they develop and move. Weather balloons launched twice daily gather data on temperature, humidity, and wind through the entire depth of the atmosphere. All this information feeds into computer models that predict where severe weather will develop hours before the first storm forms. When conditions look favorable for tornadoes, meteorologists at the Storm Prediction Center issue outlooks. These come out days in advance, giving people time to prepare. The outlooks get more specific as the day approaches. Slight risk, moderate risk, high risk. Each level tells you how likely severe weather is and how intense it might be. These aren't guesses. They're based on decades of pattern recognition, comparing current conditions to thousands of past events. The system has gotten remarkably good at identifying dangerous days before they happen. As storms develop, local weather offices take over. Meteorologists watch the radar in real time, looking for rotation signatures. When they see signs of possible tornado formation, they issue tornado watches. This means conditions are right. Stay alert. Keep your weather radio on. Know where your shelter is. If rotation tightens and a tornado becomes likely or is spotted, the watch upgrades to a warning. Take shelter now. This tiered approach gives people maximum time to respond without causing constant panic. The warning system has improved dramatically over time. In the 1950s, average tornado warning lead time was less than a minute. People had almost no time to react. Now, the average lead time is around 10 to 15 minutes. Some warnings come 20 or 30 minutes before a tornado forms. This improvement has saved countless lives. More warning time means more people reach shelter safely. The technology keeps advancing. Phased array radar, which updates every minute instead of every few minutes, is being tested. Dual polarization radar can distinguish rain from hail from debris, helping confirm when a tornado is on the ground. Storm spotters add human observation to the technological network. These are trained volunteers who position themselves safely and report what they see directly to the weather office. A spotter can confirm a tornado is forming before it shows up clearly on radar. They provide ground truth that no technology can match. During major outbreaks, hundreds of spotters might be active across a region, creating a human sensor network that fills gaps in radar coverage. Shelter technology has improved too. Building codes in tornado-prone areas now require stronger construction. Safe rooms are becoming common, small, reinforced spaces within homes that can withstand even violent tornadoes. Schools have tornado shelters. Mobile home parks install community storm shelters. The engineering is sophisticated, using concrete, steel anchors, and specific designs tested in wind tunnels. These shelters work. People who reach them survive even direct hits from strong tornadoes. The combination of better warnings and better shelters means tornado fatalities have decreased dramatically despite population growth in tornado-prone areas. The system isn't perfect, but it's effective, layered, and constantly improving. We return to where we started. Warm air meeting cold air. The simple conversation that creates tornadoes happens constantly, all over the world, usually producing nothing more than clouds and rain. But sometimes, the conditions align perfectly. The rotation develops, the funnel descends, and for a few brief minutes, the atmosphere demonstrates what it can do when energy concentrates into a tight spiral. Then it's over. The air returns to being just air. The winds scatter back into the broader patterns of weather. The tornado existed, made its mark, and dissolved back into the sky that created it. Understanding tornadoes this way changes them. They're not monsters or punishments or random acts of chaos. They're natural events, following physical laws. They're predictable in their patterns, even when specific occurrences remain uncertain. They're powerful but limited, brief but intense, dangerous but manageable with knowledge and preparation. Most importantly, they're rare. Most of Earth never sees them. Most days in tornado country pass peacefully. The odds favor calm over chaos, safety over danger, ordinary weather over extraordinary spirals. The air around you right now is the same air that forms tornadoes. The same molecules, the same physics, the same basic elements. But right now, it's still, it's peaceful, it fills your lungs gently, supporting your life without drama or violence. This is the default state. Calm is normal. Tornadoes are exceptions. Brief moments when the atmosphere needs to correct an imbalance quickly. Then, calm returns. Always returns. The spiral unwinds. The energy disperses. And what remains is just air, invisible and quiet, exactly as it should be. If tonight's journey through tornado science brought you some peace, some understanding, maybe even helped you see these storms differently, then please subscribe to this channel. we explore science for sleep every night, finding the calm curiosity in topics that often carry fear. Hit that like button and join our community of night learners who find rest in understanding. And leave a comment below. Tell me where you're watching from and what time it is there. Let me know if tornadoes feel different to you now. I love hearing from you across all these time zones. Knowing these quiet conversations about science are happening in bedrooms and living rooms around the world. Tomorrow night, we'll explore something else. Another piece of the natural world that seems complicated until you look closer and find the simple elegance underneath. Every night, a new topic. Every night, science designed to help you rest while you learn. So, give this video a like and subscribe if you haven't yet. Don't miss what's coming. For now, let yourself settle. The day is done. And as you drift towards sleep, carry this understanding with you. Even the wildest weather follows simple rules. Even tornadoes, in their spiraling dance between earth and sky, are just air talking to air, warm meeting cold, in a conversation as natural as breathing. Sleep well.